Okay, so we're still going to be talking about area underneath the curve, and we're going to talk about Riemann sums and the integrals and all that. It's all the same. But this time I want to put it in terms of the context of something. So here's a graph. The y-axis is represented by velocity in feet per second. The x-axis is represented by seconds. If I find the area under the curve, we've talked about this a little bit already, then what happens is I'm finding, like if you think about rectangles, I'm taking the x-axis and the y-axis and I'm multiplying. If I multiply feet per second times seconds, I end up with feet. So if I find that area, I'm ending up with feet, which represents distance. So if I wanted to know how far I traveled from 0 to wherever this value is, then I would find the area underneath the curve, as long as the curve is the velocity or the derivative, and that would give me the distance that I traveled. So here's another example. So it gives me the velocity, 3t plus 2. I'll go ahead and graph it. Looks kind of like that. It's in feet per minute. The x-axis is in minutes. And it wants me to estimate the distance traveled from 0 to 2. Now, because they didn't tell me how, I'm going to do left and right and average, or you can do trapezoid, whichever you prefer. So I'm going to go ahead and find, I know that 0 is 2. I know that 1 would be 5. 2 would be 8. And you could do more rectangles, but unless it tells you otherwise, just using 1 as the width is okay. So the left-hand sum is going to be 2 plus 5. The width is 1, so just 2 plus 5. The right-hand sum is going to be 8 plus 5. And then so our estimate is going to be adding those two numbers and finding the average, which we get 10. And then let's think about the units. This is feet per minute and minute. If I multiply feet per minute times minutes, I end up with feet. So this is 10 feet. And it's important to think about the units that way because it won't always just cancel out like that. There's some other things you have to do. So basically what we did is we found the left sum, which was 7. Then we found the right sum, which was 13, and then we averaged it. If you did trapezoid, you should still get the same. So still really no different, it's just that we're including units now. Alright, another problem. Estimate the total distance from 0 to 18 using a right Riemann sum. Notice that t is in minutes and velocity is in feet per hour, which is kind of strange. We'll talk about that in just a minute. Pretend like you don't know anything about the units. Let's just estimate the distance. Right Riemann sum means I'm going to start with 30, and then I need to see how wide it is. Well, it's 3 wide. Then I'm going to go to 45. It's 5 wide. Then I'm going to go to 25, and it's 10 wide. So I can't just add them and multiply. I've got to think about the width since they're different. So I'm going to have 25 times 10 plus 45 times 5 plus 30 times 3. And then I'm going to multiply that out, see what I get. And I get 565. Now, think about our units. When you've done all those rectangles things, you've done the length and the width and you've multiplied. So I've multiplied feet per hour times minutes. So right now I have 565 feet per hour minute, which really doesn't mean anything. We're trying to find the distance, so we know we got to get feet. So that means that I got to multiply by something where the minutes will go away and the hours will go away, so I end up with feet. Well, there's 60 minutes in an hour, so that means that I need to take my 565 and divide by 60. I get 9.416 feet. So you do need to check units, make sure that they match up, and if they don't, you've got to change them. All right, there's more terminology I want to talk to you about. Here's a graph of velocity, feet per second and seconds, so everything's good. If I just find the area from 0 to 6, I'm going to get 9, because there's a 4 there and a 5 there. Now, change in position is different from total distance. Total distance is like if you look at your odometer when you start going, and then when you get back home, if you look at your odometer again, it's the difference in how much you traveled, whether you traveled forward or backwards or wherever. So your odometer reading is your total distance. Your change in position is where you are compared to where you started. For example, if you started at home and you ended up at Fair Value, and then you come back home, your change in position at the very end is 0 because you're back where you started, even though you traveled a certain amount of distance. So change in position represents the integral, which means you have to consider that you went backwards. So in this particular problem, we went forward 4, and then we went backward 5, but since it's below the x-axis, so our change in position is -1 feet. So I started somewhere, I went forward 4 feet, and then I went backward 5 feet from there. So now I'm -1 feet away from where I started, which means I'm backwards from where I started. That's called change in position, which is the same as the integral. Total distance, again, is 9. It's the same as the area. So I went forward 4, I went backward 5, but the total distance I traveled was 9 because all of that was part of the distance. So I just wanted to make sure that you were aware of those, the vocabulary words, the words that you might see, change in position and distance. I have heard somebody call change in position displacement. I think in physics, some of you maybe have heard that, displacement. Displacement is basically where you are at a certain time, and that represents the change in position. All right, lastly, just a different kind of problem just to kind of talk to you about. There's 2 cars. We have car A, which is the constant graph, that line, and car B, which is that curve. And so the first question says, which one of these cars traveled farther? Well, that's talking about distance. So if I think about car A, the distance car A traveled is the area of that triangle. If I think about car B, the distance car B traveled is the area of that part of the circle. Well, which one has a bigger area? Car B does. So car B must have traveled farther. We don't have to find it, it just says which one. Okay, which one stops first? Well, it stops when it ends here on the x-axis. So A stops first because it stops before B. Maximum velocity. So the velocity is represented by the y values because that's feet per hour. And so the one that has the biggest velocity, the one that has the maximum velocity, is car A, because it starts way up here, which is a bigger velocity than car B all the time. So just wanting you to kind of see that in terms of 2 cars and trying to think about it in terms of the distance and the velocity. That'll be all. No try problems today.